Okay, so today we will discuss time series analysis, and this is time series analysis session 1. Okay, so this section is slightly complex discussion if you compare with other topics that you have studied so far. And I have found students struggling when they try to read or watch videos in this section. The problem with this topic is that it is an amalgamation of very small concepts in statistics. So you need like understanding of regression, quite detailed understanding of regression. And because we have done regression in depth, so it would be easy for you to understand. But the reason it is complex because until unless you haven't studied applied statistics, as in quantitative analysis in detail, applied statistics in finance in detail, if you don't understand normal distribution, if you don't understand hypothesis testing, if you don't understand the regression, it is very difficult to pick this topic. So what I did today that I have summarized this topic in a story, in a flow chart. So if you study and if you can concentrate for 30 minutes, in 30 minutes, we'll try to understand that story, we'll try to understand that flow chart. And it would be very simple for you to pick this topic at even at your own level if you have watched this session for 30 minutes. So be attentive for the first 30 minutes. Okay. Now, the agenda of this topic is very simple and straightforward that we have to study different models in time series analysis. Different models in time series analysis. So there are trend model, there are ARMA model. In trend model, we have to study two model, that is linear trend model and log linear trend model. In ARMA model, ARMA stands for autoregressive moving average model. So autoregressive model and moving average model. So first of all, we'll understand these models. Linear trend model, log linear trend model. Linear trend model and log linear trend model falls under the category of trend model. And then you have ARMA model, where you have AR, which stands for autoregressive, and MA, which stands for moving average model. So first of all, we'll try to understand these four models. Now, what is critical in any model is to understand the properties related to that model. So properties in time series that should hold true, should not hold true. So that is what covariance stationary. So we'll study about covariance stationary property of ARMA model, why we need a time series to be covariance stationary. And then we'll understand what is the problem of unit root. And we'll also understand something called as white noise and Gaussian white noise. And the last, we'll understand the different hypothesis testing. As we studied in the regression models, we'll study the hypothesis testing in the time series analysis. So this is the agenda. Okay. So as I stated that in time series analysis, there are two models that we have to understand. The first model is trend model. In trend model, we have two models. One is linear trend model, another is log linear trend model. Then another set of model that we have to understand is ARMA model. AR stands for autoregressive, MA stands for moving average model. Okay. Now, however, if I have to define what is time series, A time series is the study of data which we are observing at equally spaced time. This equally spaced time is very critical. So if you're studying any data, any historical time series, any time series, say that is xt, and we would be plotting it against what? Time. If I'm writing 1, 2, 3, 4, 5, 6, I don't know what 1 represent, 2 represent, 3 represent. If it is month, it has to be equally placed. If it is year, it has to be equally placed. If it is seconds, it has to be equally placed. And then you observe the data point. If it is not equally placed, you will not be able to analyze the time series, analyze a sequence of data. So it has to be what? Equally spaced in the terms of time, any data, whether it is stock price, whether it is GDP, whether it is interest rate, whether it is inflation. So what I'm trying to say that, okay, if you are studying stock price, okay, stock price of today, yesterday, day before yesterday. So what is the time interval? 1 day. So equally spaced time intervals. Okay. This is the definition of time series. But what we are analyzing in time series, what we are actually analyzing in time series, what we are trying to analyze. Any time series, we are trying to analyze four component in that time series. Whether that time series has a trend or not. Trend. Whether a time series has a trend or not. Increasing or decreasing with time. A trend or not. Whether the time series has seasonality or not. Whether the time series has a cyclical nature or not, and whether the time series has a randomness or not, and whether the time series is dependent upon the randomness in the data or not. Okay. So when you hear this trend, we are talking about what? Trend model. When you are hearing about cyclicality, we have to study autoregressive model, AR model, and a bit of MA model. And when we are saying that let's study whether my time series is dependent upon the historical shock, then I'm also studying moving average model plus the randomness in the data. So if you want to be best in time series analysis, then you always try to understand the time series, any time series, whether it is stock price, bond price, any time series on 4 scale, whether it has trend or not, whether it has cyclicality or not, whether it has seasonality or not, whether it has randomness or not. And what is seasonality? We all understand what is seasonality. We all know that in December, the sale of or the demand of gold increases. Why? Because of festive season, because of wedding, whatever. So whether the time series has seasonality or not. Okay, so these are the components. If you understand well, you understand time series analysis and you can predict the future of that entity that you are analyzing. So you would be able to predict X. You would be able to predict stock price or stock return if you can understand these four components well. And each component represent a model. Each component represent a model. When I said cyclicality, I'm talking about past values or past shock. So if you want to study past values, you will study autoregressive model. If you want to understand how the time series get impacted by past randomness or shock, you will study moving average model. When you want to study both past value and past shock, how it is impacting your X, you will study ARMA model. When you try to understand the seasonality with past shock and past value, you would say seasonal ARMA model or seasonal ARIMA model. ARIMA model is nothing but it is differencing. So therefore, I'm not worried about whether you understand I in the ARIMA model. You need to understand ARMA. I is not that much important. And definitely, if you understand these four model well, you can understand any time series model properly. Okay? It covers everything. It covers seasonality, it covers trend. Actually, trend is not written there. Trend, it covers cyclicality, and it covers randomness. Cool. But what I stated at the starting that time series analysis is dependent upon a concept of regression. So we'll try to build analogy and we'll try to build our concept from regression. Cool. So till now, I was giving you a summary of time series analysis, what we are studying, what we have to study. We are starting the topic now. Okay. In regression, what we say? In regression, we say that y is a what variable? Y is what variable? Dependent variable. And what is x? And x are independent variable. Actually, y is dependent upon x, but x has no intuition about y, as in x is not worried about y. And that's why it is independent variable. So we are talking about, can I predict y with the help of x? That was regression. For example, we did the exercise of predicting stock price with the help of GDP of the country, interest rate in the country, R&D, investment of the firm, management quality of the firm, blah, blah, blah. GDP, interest rate, inflation, management, or R&D, all are independent variable. And we call it X. That was a regression. How time series analysis is different from regression. Time series analysis says, okay, let's predict Y, but with the help of time. Again, time is an independent variable, but it is a class of independent variable, time. A very weird independent variable, which is constant in this world for everyone, for every country, for every firm, for every human being. Very weird independent variable. So I'm saying with that help of that independent variable, I'm trying to predict my Y. And that give rise to another study, that is time series analysis. Perfect, no issues. Now this time series analysis, when I say that my Y is directly, what? Directly dependent upon time. Directly dependent upon time, where I can write Y is a function of time. And I can expand that function and say Y is equal to beta naught plus B1 into time directly. This is the study which is called as trend analysis. When I say Y is indirectly dependent upon time, indirectly, I cannot directly write Y is a function of time, but I can write Y is a function of past values. So it is an indirect relationship. So what I'm saying, my y is dependent upon the past values, and these past values, because I said past, how can I say past until unless I have a sense of time? So definitely we are talking about time, but in a indirect sense. So when I can write directly y is a function of time, perfect. That is a trend model. When I cannot write y directly as a function of time, but y is a function of past values, then that is ARMA model. See, I can write y as a function of time, y as a function of time. I can directly write time. That is a trend model. But here what I'm saying, yt is dependent upon the past value of yt, the previous value of yt. So your stock price today is dependent upon what happened yesterday. Your interest rate today is dependent upon what happened yesterday or day before yesterday. Or your yt is dependent upon what was the randomness in the prediction for the yesterday, or what was the error in prediction yesterday. So still it is dependent upon time, but indirectly. And that is ARMA model. So ARMA model is about past, trend model is about y directly dependent upon time. Time. Time will come as a factor, as an independent factor. So that is the difference between regression and time series analysis. So I can say that time series analysis is a subset of regression. If I'm saying that time series analysis is a subset of regression, then I have to remember all the assumption that we have studied in regression, and it has to hold true, but not every assumption, because the entity is very different. It is time, and you have to respect time. Literally, you have to respect time here and say that, okay, because it is time, it is not any other entity. It is the most important resource of this planet for a human being, that is time. Therefore, you have to tweak certain assumption, but have to respect certain assumption that you discussed in regression. So the question is, what is the first assumption that I repeated 100 times in regression? What was that assumption? Very good. Error term is normally independently distributed with a mean of zero and a constant variance. Or actually, I used to say error term is independently normally distributed with a mean of zero and a constant variance. Everyone remember this assumption repeated 100 times? So let's write this assumption. Let's write this assumption. So assumption is error term is independently normally distributed with a mean of zero and a constant variance. This was the first assumption. So what time series is saying, do not respect other assumption, but you have to respect certain part of the first assumption. And that is error term has to be independently distributed. I deleted the word normality, mean equal to zero and a constant variance. If I combine these three words, independent, mean equal to zero, and a constant variance, in statistics we call it as In statistics, we call it as white noise. And white noise does not have any relationship with error term. Error term could be white noise, but anything on the planet could be white noise. I can write xt could be white noise, yt could be white noise, error could be white noise, kt could be white noise. Any entity, zt, any time series could be white noise if it is independent. What is the meaning of independent? What is the meaning of independent distribution or independent? What is the meaning of word independent? What is the meaning of word independent? That the correlation of that entity with anything on the planet is zero. Anything on the planet is zero, even with itself. It cannot be dependent upon itself. So you cannot predict xt with the help of xt minus 1 or yt with yt minus 1 if that entity has to be called white noise. If you're calling that entity white noise, it is not dependent upon anything on the planet. It is random, purely random. Okay? Then mean equal to zero and a constant variance. That is called as white noise. What we are saying that the error term in a regression has to be white noise plus normally distributed. Now, when you add normality to a white noise process, to an entity which is following a white noise process, we call it as Gaussian white noise. Why Gaussian white noise? Why Gaussian white noise? The reason is Carl Gauss has given the PDF, the CDF that you study now about the normal distribution was given by Carl Gauss. So the name of this distribution came from Carl Gauss, and that's why we call normal distribution as a Gaussian distribution. Okay? So we call it as Gaussian white noise. So if I say that in a regression, the error term has to be white noise or a Gaussian white noise? Gaussian white noise. What? Gaussian white noise. So the assumption is Gaussian white noise in regression. The same white noise has to be respected here. Same assumption has to be respected here in the time series analysis. Okay, and that assumption is that error term either have to be white noise or a Gaussian white noise. Where it has to be white noise and where it has to be Gaussian white noise, we'll study it later. We'll understand it later. But it has to be Gaussian white noise. So what I'm trying to say you have written this equation. You have written this equation that okay, in the trend model, there is yt is equal to beta naught into beta naught plus b1 into time plus error term. This error term, this error term, this error term, this error term, this error term has to be at least white noise. And in some cases, it has to be Gaussian white noise. Clear? So what we are doing, we are trying to borrow some concept from what? Regression into time series analysis before even deep diving into time series analysis. So understood what is white noise and what is Gaussian white noise. It is nothing new. I'm just giving a terminology which we have studied in regression. Clear? Understood? Now, just to respect the slide, let's read what is written for white noise. A series which is serially uncorrelated, which means what? What is the meaning of serially uncorrelated? In our terminology, it is independent. With a mean of zero and a constant variance, we call it as white noise process. If that process follows a normal distribution, it is called as normal white noise or Gaussian white noise. Generally, people call it Gaussian white noise. You can also call it as normal white noise. There should not be any pattern among the time period. So xt would be completely what? Random. Et would be completely random. It could be anything on the planet. And that is what is the definition of a white noise process. Cool. Now, there is a problem with the time series analysis. The problem is it has so many moving concepts. It has so many moving concepts that you will never be able to remember this session after 10 days. It is impossible. Until unless you summarize the whole story in a flowchart. And this is that flowchart. If you understand this flowchart, and the next time if you want to revise the time series analysis, the only thing that you have to do is to watch this section of the video. That's it. And then you can read the book or whatever you want to do. So this is the essence of the discussion. So I'll start with this essence. We'll start with this crux. Start with this flowchart. And if you understand this flowchart, you will never struggle with time series analysis. The best part is you try to write this flowchart at your own level in a notebook or whatever and try to revise it for the next 2, 3 days. That's it. And you will never ever forget time series analysis in your life. Okay? You have to be bit interactive because I haven't talked about what is trend model, what is ARMA model. I have just given you some word about it. So to make it this flowchart, make it like very intuitive when we would do the discussion, just be a bit interactive. Design a trend model. What is a trend model? What is a trend model? Where Y is directly dependent upon time. What are the two trend model we have? Do you remember? What are the two trend model we just saw? Yes, linear and log linear. Have we studied them? No. We'll study in depth, but at least we know the term linear and log linear. Trend model, linear trend model, log linear trend model. We have to study it in depth. The question that you have to ask is whether the error in these model follow white noise or not. We studied this, yes or no? Error term has to follow white noise or Gaussian white noise. What is written here? White noise. If it follows white noise, awesome. Yes, it follows white noise. You can use the trend model, whether it is linear or log linear. What you have to test for? You have to test for whether error term follow white noise process or not. And I have not written what? Gaussian white noise. So that is not a condition. That is requisite to use the trend model. Perfect. If not, if it doesn't follow white noise process, no, it doesn't. Actually, you have to test something in Y, not in error term. The Y you are trying to predict. You have to test something. That is covariance stationarity. What? Covariance stationarity. Whether what you're trying to predict, if it is Y you're trying to predict, if it is Y you're trying to predict, if it is X that you're trying to predict, if it is Z that you're trying to predict, whether that follows covariance stationarity or not. Have you studied covariance stationarity? No, we haven't. Just remember this word, covariance stationary. That's it. We'll study it in depth. If it doesn't follow covariance stationarity, the thing that you're trying to predict, you can't use any model on the planet. Sit at home, you can't use any model. Story ends there. If the error term does not follow white noise, check for whether Y is covariance stationary or not. If it is not, you can't use any model. Story ends. But if it does, then you can design AR, MA, or ARMA model. What is ARMA model? What we have studied about the ARMA model till now? Till now, what we have studied. We have to study ARMA model in depth, but what we have studied till now about the ARMA model? Dependent upon the past value. Yt is dependent upon itself, yt minus 1. That kind of model. A yt is dependent upon the previous error term. That kind of model. Not directly dependent upon time. So you can fall back to another model because now you cannot use trend model because error term does not follow white noise. You go for another model. But when you're using another model, when you're designing another model, the error term of that model has to be what? The error term of that model has to be what? What we borrowed from regression. What we borrowed from regression, white noise. So you check for white noise, but there is a restrictive condition. Not only white noise, it has to be Gaussian white noise. So whatever you respected in regression, you have to respect in the ARMA model, but not in the trend model. Follow Gaussian white noise. Yes, awesome. Use the model. No, you can't use any model on the planet. Stop there. Till now, the flow is clear. You don't need to remember this section. Till now, the flow is clear. You don't know what is covariance stationarity. That's fine. But at least the structure of the session is clear or not. It's clear. Now, there's another test that is required in the ARMA model is that whether there is a problem of unit root or not. Unit root. Unit root or a problem of randomness. What is the problem? Problem of randomness. Unit root and randomness are the same entity, only different terminology, different name. You called Ram, you called Rama. Doesn't matter. It is the same thing. This is randomness. Unit root problem, the problem of randomness. If there is a problem of randomness, if there is a problem of, yes, there is a problem of randomness, you can't use the model. You have to resolve something called as first differencing. And if it is resolved, then only you can use the model. If there is no problem of randomness or unit root, you can use the model. If you don't remember this section right now, doesn't matter. What matter is this flow and this. With this, we can start the session. Okay, cool. This is the flow chart. You will revise just before the examination or whenever you want to start studying time series analysis again. So what we did, whatever we are going to study for the next 2 hours, 3 hours, whatever, we have summarized it in in the discussion that we did in the last 5 minutes. Cool. Okay. So what are the words that we have to understand? Definitely we have to understand what is trend model, ARMA model, AR model, MA model. But we have to understand this word covariance stationarity. We have to understand this word unit root. We have to understand this word first differencing. And we'll study these terminologies. Okay, cool. With that, we entered into the first model, that is the linear trend model. The linear trend model. The simplest of all, the easiest of all. So because the trend is written, I can say directly y is a function of time, or I can write y is equal to beta naught plus b1 into time. It would be y hat if there is no error term. Otherwise, I will write y is equal to beta naught plus b1 into time plus error. So yt is equal to beta naught plus b1 into time plus error term. So let's put down some values like beta naught could be 4, b1 could be 5 into time. That is my y hat, and there is always an error in prediction. What do you feel? This is an equation of a line? Yes or no? This is an equation of a line. So when you plot it, definitely you will get a line. The way you used to get a line in regression. But what this equation represented, this equation represent that if time is 1, what would be the value of yt? Hat actually. What would be the value of yt? 9. Time is 2. What is the value of yt hat? 14. 3 would be 19. 4 would be 24. I'm asking a question. Does this equation represent a growth in a constant amount or constant rate? Does this represent a growth in the terms of constant amount or constant rate? Think carefully. So what is the difference between the two? 5. What is the difference between the two? 5. What is the difference between the two? 5. Is it constant amount or constant rate? What is the definition of rate? Growth rate. When you write growth rate, you write what? Current value minus previous value upon previous value. Is it a constant rate or a constant amount? It is a constant amount. So when you're writing the linear trend model, it does not represent constant rate, it represents a growth of a constant amount. Actually, if you look carefully, there is a decreasing rate. If you look carefully, there is a decreasing rate in this one. So why it is a decreasing rate? Because you have written 1, 2, 3, 4, 9, 14, 19, 24. Let's try to find out the rate here. 14 minus 9 upon 9 is going to be 5 upon 9. And this would be 19 minus 14 upon 14. This is going to be 5 upon 14. This is going to be 5 upon 19. Can you see that the growth rate is actually decreasing? Can you see 5 upon 9, 5 upon 14, 5 upon 19? The growth rate is decreasing. Yes or no? You can see that? Okay. So there could be a question in the examination whether the linear trend model has a constant rate or a constant growth amount. Let's try to fill this values as in y hat is equal to minus 10 plus 2.5 into t, and actually there shouldn't be error term because it is what it is. It is y hat. So can you fill this value? What should be the value here? Yt is equal to minus 10 plus 2.5 into t, and time is 1. Then this value would be how much? Minus 7.5. For 2, the value would be minus 5 and minus 2.5. Now the actual y could be different. You can see the actual value could be different. So this can come as what? Minus 8. This can come as minus 7. This can come as minus 3. And there is error in prediction. And there has to be error in prediction. Your model cannot be perfect. You're not got to see to have a view about the future, or you don't have the crystal ball to see the future. So there would be error in prediction. And what is the error in prediction we write as? Actual minus predicted. Actual minus predicted. Actual minus predicted. And that's why whenever we write the model, we write what? We respect this error, because there would always be error in prediction. And that error has to follow what? That error has to be what? Completely following what process? White noise process. Easy. Now, how many times in the real world you have seen that stock price is linearly increasing or linearly decreasing? How many times have you seen this? Can you all hear me? So the question was how many times you have seen stock price or anything on the planet linearly increasing or linearly decreasing? Not never, but hardly. Definitely hardly. Once in a blue moon, once in a year, or once in a month. There would be a very short period of time you observe that the stock price is linearly increasing or linearly decreasing. That happens, but for a very short period of time. So this model, this linear trend model has to be respected when you actually can see or observe a linear trend, which generally be in the real entity for a very short period of time. But very much related to time, we see an exponential growth in a firm or exponential decay in a firm, maybe at the starting phase of the firm or maybe when it is reaching a collapse. So for that, there is another model that is exponential increasing or exponentially decreasing model, which is called as a log linear trend model. Why we call it log linear, we'll talk about it, but actually intuitively, this model is exponential model. Exponential model. Because when you write your y is dependent upon time, you say it is exponentially dependent upon time. Either it is increasing exponentially or it is decreasing exponentially. So the equation would be exponentially increasing with time or exponentially decreasing with time. When it is exponentially increasing with time, this is a good representation of pictorial representation of a log linear trend model or exponential increasing time series, or it could be exponentially decreasing. Okay. Now, why it is called as log linear trend model? What is the problem in writing y is equal to beta naught plus b? Sorry. What is the problem that we respect e to the power something in this model? What is the problem? Why we cannot write the model like this? What is the issue? What is the issue? What was one of the assumption of regression that should hold true if you're applying ordinary least square method to find your equation? You remember the assumption, one of the assumption of regression that we discussed? Because if it is not true, whatever the assumption is, you have to tell me the assumption. If it is not true, if that assumption is not true, you cannot find the equation of a line through ordinary least square method. What was that assumption? Can you all hear me? What was that assumption? That assumption was linearity in parameters. Linearity in parameters. When you write in this format, your parameters actually not have a linear relationship or does not follow the linearity. It is on a power, e to the power something. So to make it linear and to find the equation of the line, you have to drop it. You have to drop it. So how can you drop it and make it a line? By taking ln both side. So when you take ln both side, you know that ln e to the power something will become what? Now it will become linear. And when it becomes linear, now you can apply OLS to find B1 and beta naught. Otherwise, you cannot do the differentiation that we did in the last session of regression and find out your beta naught and beta 1. So therefore, it is not called as exponential model. It is called as a log linear model because your beta naught beta 1 was at a power, e to the power something. And that does not respect the property of linearity in parameters, and therefore it has to be dropped and become what? Linear. Now you can use OLS and find beta naught and beta 1. So therefore, the way this model is generally written, the equation is written as not y is equal to e to the power beta naught plus b1 and something, but it is written in the format of ln of yt is dependent upon time in a linear format. Okay. Okay. Again, same thing. One, two, three. Can you give me the value of y hat? E to the power minus 7.5, e to the power minus 5, and e to the power minus 2.5. Is it correct? These are the values of y that you will predict from this model. Yes, no? Yes. Now again the question. Can you see a constant amount or a constant rate? Can you see a constant amount increase in the value of y based on a constant amount or a constant growth rate? A very simple question. Whenever you see anything exponentially increasing, you say it is increasing by a constant growth rate or a constant amount. What do you say generally? You say constant rate. So definitely it should be increasing by constant rate. Can we check it? Yes, let's check it. So previous value minus initial value, e to the power minus 5 minus e to the power minus 7.5 upon, sorry, upon e to the power minus 7.5 is equal to what? E to the power 2.5 minus 1. What is the difference between the two? E to the power minus 2.5 minus e to the power minus 5 upon e to the power minus 5. This will be again e to the power 2.5 minus 1. Can you see that it is increasing by a constant growth rate? The reason is if you do et plus 1 minus et upon et, every time it will come as e to the power 1 minus 1. Okay. So therefore, this is increasing by a constant rate. It can also decrease by a constant rate. If it will decrease by a constant growth rate, how can I change this equation and get a decreasing constant growth rate? What I have to change in this equation? What I have to change in this equation? One thing that I'll change in this equation, and this will become a constant decreasing growth rate. Yes, that is the only thing I have to do. I have to change the sign and make it negative. And same thing here. If I have to make it decreasing, what I'll do, I'll make the slope of the line negative, right? So this is the trend model. And the trend model, we have two trend model. One is the linear trend model and another is a log linear trend model. Let's see what is the core written in your curriculum. Changes by the same amount. It could be an increasing or a decreasing line. We are talking about which model? Linear trend model. What is linear trend model? Where the equation is yt is equal to beta naught plus b1 into t plus array term. No exponential terms, no ln term. It changes by same amount, not same growth rate. It could be an increasing line or a decreasing line. Error term should not be, should be white noise process. And Gaussian is not a requisite term here. What is the benefit? It is very simple to understand, simple to put it in the model. The problem is, first of all, if you're applying it for a downward sloping linear trend model, then what it predicts negative value. Negative value for something which can't be negative. For example, if you apply for stock price and stock price is falling, actually it is predicting after a certain time period, it would predict what? That the stock price can go to negative. Okay, and that is the problem with the trend model. And the other problem with the trend model is that you hardly see for a very long period of time. You see the trend model for a very short burst of time, very short interval of time. So therefore, we have to move and become advanced and make use of those model, which is actually you see in the general real life scenarios. Okay. In the log linear trend model, what are the components written as? The component written as that linear or non-linear trend model are estimated by a regression, that is ordinary least square method. So therefore the error term should be what? White noise. If if your time series is detrended, then you cannot use this model. What is the meaning of detrended? We already studied. If it is not white noise, but Cohen is stationary. If it is not white noise and Cohen is stationary. If it is not white noise, but your time series is covariance stationary, we call it as detrended, which means that you cannot apply the trend model, which we already studied. That if error terms follow white noise process, does does not follow white noise process, but what you're trying to predict, your y is covariance stationary, then you cannot use the trend model. You have to use what? ARMA ARMA model. And that is what is written here as a one liner in your curriculum, that if your y is covariance stationary, but the error term is not white noise, use ARMA ARMA model. Okay, and what it represent? It represent a constant rate of growth. It could be positive, it could be negative. Okay, I'll pause here. Any doubt in log linear trend model or linear trend model? Both, both, both. It is for both. This flow chart represents everything. The snippet that you see, the section that you see that I was discussing is a snippet from your book. So trend model was easy, simple. Any doubt so far? Okay. Now, when we fall back to ARMA model, we designed a trend model. What we have to check in the trend model? What was the flow chart? You have to check for whether it follows white noise or not. If yes, awesome, you can use the trend model. If no, what you have to test? Okay, you have to test stationary covariance stationary property of what? Error term? No, why? This is the biggest mistake that student does. You have to check the covariance stationarity property of y, not error term, the thing that you're trying to predict, whether it is covariance stationary or not. If yes, then only you will fall to ARMA model, whether it is autoregressive or moving average model. Clear? I'm repeating the flow chart. You designed the trend model. You designed the trend model. Error term was not following white noise process. You will test for whether Y is covariance stationary or not. If yes, you design ARMA model. Yes, you again have to test whether the Gaussian white noise process has been respected or not. But you cannot touch ARMA model or ARMA model until and unless Y is covariance stationary. Y has to be covariance stationary. Otherwise, you cannot use ARMA model. Any model that falls under ARMA model. But what ARMA model represents? What is ARMA model? So first let's talk about AR model. Let's break ARMA into AR and MA model, and first we'll discuss about AR model. First we'll discuss about AR model, that is auto-regressive model. What it says that YT is dependent upon or is a function of, the easiest way to write it as, the YT is dependent upon itself or its past value. Basically, Yt is dependent upon Yt minus 1, or Yt could be dependent upon Yt minus 1 and Yt minus 2, or Yt can be dependent upon Yt minus 1, Yt minus 2, Yt minus 3, or Yt can be dependent upon just Yt minus 2. I am dependent upon myself. That is autoregressive model. I am dependent upon myself. Autoregressive model. Now, in the autoregressive model, if I write the equation yt is equal to, it is dependent upon its previous value, beta naught plus b1 into just the previous value, lag 1, as in yesterday value. When I say lag 1, I'm talking about yesterday's value. So stock price today is dependent upon previous day stock price, just the previous day stock price. And definitely there would be error in my prediction. This model is called as AR1 lag model. AR1 lag model. AR1 model. Autoregressive one model. But when I say no, Yt is dependent upon two things. It is dependent upon Yt minus 1 and Yt minus 2. As in it is dependent upon the previous day value and the previous to previous day value. So 2 lag. So Yt is equal to beta naught plus b1 into Yt minus 1 into b2 into Yt minus 2. We'll call it as AR2 model. What should we call it? What should we call it? How many lags do you see? What is the extreme lag that you see? 2. So I'll call it as again AR2 model. This is also AR2 model. This is also AR2 model. So you have to talk about the maximum lag. And this is AR3 model. Okay. But the question is, I can only go for this model I can only go for this model when when I can go for this autoregressive model when my y, which I'm trying to predict, whether it is stock price, inflation, GDP, interest rate, anything on the planet, is covariance stationary. What is the meaning of covariance stationary? What is the meaning of covariance stationary? This is a very extreme example of covariance stationarity. If you see this red graph, red curvature, this is actually your y. What is the observation? Can you tell me about the observations? This is your y. What you felt about this y? Cyclical. Good. Awesome. So I'm writing the word cyclical. This is your observation number one. What are the other observation others? Cyclical. What else? What is other observation? Awesome. What is constant? The range of y is fixed, not growing. Basically, I'm writing it range of y. Good. This is another. What is constant? Prasanna, you stated constant. What is constant? What is the third? Range is constant. Range of y is constant. Awesome. The value yt is clustering. Clustering. What do you want to say by clustering? I'm writing clustering, but what do you want to speak about clustering? As in, can you elaborate the word clustering? What else? What other observation? Okay. In statistics, when I say cyclical, and if you look very carefully this graph, can I say this is mean reverting? Can you see the mean? Can you see this y is actually mean reverting? I'm writing this term clustering because the way you have spoken clustering is not the right thing, but what you have stated and elaborated is correct. So I would delete clustering and I would write what Amit has just stated, that is same in different time period. This is actually a property, but we have to just give the right nomenclature. It's not clustering, it's something else. When I say cyclical, and when you see this, can I say it is mean reverting? Yes or no? Can I say this is mean reverting? Yes or no? Everyone can hear me? Others, can I say it is mean reverting or not? Only one answer. Others, it is mean reverting. When I say it is mean reverting, it can only be mean reverting if its mean is actually constant and finite. It's stable and finite. Can I see that mean? This is that line. This is that mean. This is the long-term mean. This is stable, constant, and finite. It is not infinite. This is one. When you say that the range is fixed. If you think from a statistician perspective, actually you're saying the variance is constant and finite. You're talking about variance. You're talking about variance because when it is growing and then decreasing, when it is growing and decreasing, that height, that dispersion from the mean is constant and finite. So the second term is variance is actually constant and finite. The third observation is same. Why is same in different time period? Super critical. It means that it means that the covariance structure, statistically you call it as covariance structure, is constant and finite. And I'm saying you can relate to these two like this. It is very intuitive. You can see the mean is constant and finite and it is mean reverting. You can see that the variance is constant and finite, but that intuition of covariance is constant and finite. I've not seen any student understanding that in the first go. That what it actually means statistically. If you look very carefully, let's cut a time. Let's cut a time frame. Let's cut this time frame. This time frame. This is the time frame I'm cutting. And I'm calling it YT. Assume I'm calling it YT. Cut the next time frame. So definitely the next time frame should have the same length. Cut this time frame. So this is calling as YT minus 1. This is YT minus 2. What it means that the correlation, when I say covariance is stable and finite, when I say covariance is stable and finite, I'm also saying the correlation is stable or finite. It means the correlation between YT and YT minus 1 is constant and finite. The correlation between YT and YT minus 1 is constant and finite. If I'm saying the correlation is 0.7, it means that if you find the correlation between YT minus 1 and YT minus 2, it is also going to be 0.7. If I'm saying the correlation between YT minus 2 and YT minus 3, it is also going to be 0.7. So basically, I'm saying that if you write YT and YT minus K, if you write correlation between YT and YT minus K, take any value of T and K, the correlation is going to be constant and finite. It also means, I'm just trying to give numbers to this, YT minus 2 and, sorry, YT and YT minus 2. Listen very carefully. Don't confuse this point. This point is very critical. I'm writing it in detail. If I'm saying the correlation between YT and YT minus 1 is 0.7, then the correlation between YT minus 1 and YT minus 2 is also 0.7. And YT minus 2 and YT minus 3 is also 0.7. And listen very carefully. And if I'm saying the correlation between YT minus 1, or even don't write YT minus 1, just write YT, and YT minus 2 is 0.49, then the correlation between YT minus 1 and YT minus 3 is 0.49, and the correlation between YT minus 2 and YT minus 4 is 0.49. And if I'm writing the correlation between YT and YT minus 3 is zero point 0.2, then the correlation between YT minus 1 and YT minus 4 is 0.2. Can you see a pattern? What is happening? What is the lag between the two? What is the lag between the two? What is the lag? What is the lag between the two? What is the lag? 1. When there is a lag of 1, whichever time section you pick, the correlation is going to be 0.7. What is the lag here? What is the lag here? Everyone? What is the lag here? 2. Whenever there is a lag of 2, the correlation is going to be constant for that lag. What is the lag here? 3. So the correlation for 3 lag would be constant. And that is the meaning of covariance stationarity. When your mean is stable, variance is stable, and covariance is stable. And that is the specific meaning of covariance is stable and finite. Clear? Perfect. Now, if your y does not follow this, then you cannot cannot have your AR model or MA model, or ARMA model, ARIMA model, or SARIMA model. Now tell me whether image 1 is covariance stationary or not. Image 1 is covariance stationary or not. Okay, so I got one no, I got one yes. Others, is image 1, this image, is covariance stationary or not? Okay, the first question. Is the variance constant? The answer is yes. The variance is constant. Even the covariance, when you calculate it, will come constant. But what is the problem? What is not constant and stable? That is mean. Can you see the mean increasing? If the mean is increasing, then how can I say that it is covariance stationary? The mean has to be stable, constant, and finite. It's not constant, stable, and finite. So this is not covariance stationary. It does not follow the property of covariance stationarity. Okay. Second, can you see this image? Second, does it follow the property of covariance stationarity? No. Why not? The mean is stable and finite. What is the problem? The mean is stable and finite. What is the problem? What is not stable? Correct. The variance is not stable. You can see it is decreasing, it is increasing. The variance is not stable. What about third image? What is the problem? Mean is stable and finite. But again, the variance, you can see the height is changing. Okay. Fourth image. What is not stable and finite? Mean is stable. What about variance? Can you see variance as stable or finite? Yes, no, please. Can you see in image 4, the variance is stable and finite? You can see that. Variance is actually stable. See the height? It is stable. So when you calculate your y minus y bar in any section, it is going to be same. So what is the problem then? What is the problem? What is the problem? The problem, you all can hear me, right? The problem is, if you take this as a complete YT series and if you try to map it with the YT minus 1, the problem that you will face that when you calculate the correlation between YT and YT minus 1, if it came to 0.7, and when you calculate the correlation between YT and YT minus 2, you can see that the whole trajectory of Y has changed. So therefore, the correlation between YT and YT minus 2 will not be 0.7. YT minus 1 and YT minus 2 will not be 0.7. It has changed. So actually what is not stable in this is covariance is not stable and constant. And therefore you cannot use this Y and do a prediction with the help of ARA or MA model. None of the model will work. So most of the time, will you always have this kind of plotting? No, you won't have this kind of plotting. You will have this kind of plotting. Yes, these kind of plottings in the real world are prevalent. If you find these kind of plotting very near to covariance stationarity, then you check. This is like a perfect example of being covariance stationarity. Mean is stable and constant. You can feel it. You can see it. Variance is stable and constant. You can feel it. You can see it. Covariance is stable and finite. You can feel and see it. And in all these plotting, you can directly see that, okay, that mean is not stable, the variance is not stable, and the covariance is not stable. But when in the real life, you will see a lot of graph like this that is moving around the mean, but in a zigzag manner. So you have to do what? You have to perform hypothesis testing to test whether the mean is stable, whether the variance is stable, and the covariance is stable. However, that hypothesis testing is not in your curriculum, that is another thing. But until unless you test for three things, mean is stable and finite, variance is stable and finite, and covariance stable is finite, until then you cannot say that the time series is covariance stationary. And until then you cannot use ARMA model. It could be even a discrete point but that is a long-term mean. This mean. So you're talking about the mean, right? This mean. Are you talking about this mean? Yes. Okay. What is the long-term mean of interest rate in India? What is the long-term mean of interest rate in India? So this mean is the long-term mean. Interest rate in India for a long-term mean is currently around 7%. So either you decrease, increase, decrease, increase, decrease, increase. The long-term mean that we have observed from the past is 7%. It is mean reverting at that point. That long-term mean has to be a point, a 1 point. But whether you're standing today, day before yesterday, day before to before, as in before yesterday, or whatever time frame, it is going to be that point. If I'm saying the stock price long-term mean is 50, it is that line. The 50 is a continuous line because it is one long-term mean that you predict with the help of the model or through hypothesis testing. Now, how we predict that Y mean we'll see in the session in just a few minutes. But that is going to be a 1 point. And when you plot that 1 point for the whole time series, it is going to be a continuous line because it's a constant point 50. How would you plot? If I say a constant value, plot 4. How would you plot 4? You will plot like this, right? You won't plot the 4, y is equal to 4, a constant value like this. Which first example? This example or this example? Even in this example, when you plot the time series, when you plot the mean would be increasing. Now that would be a discrete point or a continuous point, that doesn't matter. Even in this point, if you plot it, it is going to be a discrete point, but how does it matter? There would be a line that is going through this. So the discussion is not about whether the line is discrete or continuous. The discussion is about whether the mean is constant or finite. It's not constant, it is increasing. Okay, so coming back to what is covariance stationarity? The mean has to be constant and finite or stable. The variance has to be constant and finite, and the covariance has to be constant and finite. It means that it only depends on lag, not on the time. Even if you remember, I have written yt and yt minus k. This t is actually irrelevant in finding the correlation. This is the k, this is the lag which tells what is the correlation is going to be. If the lag is of 1, the correlation was 0.7. If the lag is 2, the correlation was 0.49. If the lag is 3, the correlation is 0.2. So that is what is written. Now, when you test this covariance stationarity, and when you find that, okay, Y is following covariance stationarity, then only you can go for AR models. Then you can go for AR model, autoregressive model. Now, because the question came about, how would you find the mean? when I was talking about the mean, how would you find the mean? So we have to study something that when you use this AR model, when you use this autoregressive model, which is like YT is dependent upon the past values, YT minus K, then what is the mean? What is that long-term mean? How can I find that long-term mean? And how it is constant and finite? Okay, so there is an equation which is given that your long-term mean is equal to this. So we'll prove what is the mean of autoregressive model, what is the variance of autoregressive model, and what is the correlation between the two lag of a autoregressive model. Okay, so till now we have only studied an autoregressive model that you can only use the autoregressive model when your y is covariance stationary. Okay, here we'll take a break. We'll take a break of like 30 minutes and then we'll start our autoregressive model. Cool. Thank you. Cool. So we have everyone. Perfect. Cool. So we were discussing autoregressive model. So few pointers in autoregressive model. We just discussed that we can only use autoregressive model if we have covariance stationarity in Y. That's perfect. That's awesome. But what is this autoregressive model? So when I'm saying YT, say YT is my stock price. So say the stock price today was 50, day before yesterday 49, 52, 48, 53, 47, 54, 46, so on and so forth. So you have to write YT minus 1. Then what I'll write YT minus 1 in front of 50 if 50 is today's price. What I'll write in front of 50 that represent YT minus 1? We write 49 because this corresponds to the previous day value. If I'm talking about t today, then the previous day value would be 49. What I'll write in the front of 49? It was yesterday. I'll write 52. What I'll write in front of 52? 48, 53, 47, 54, and say this is 46. Here it will be blank because I don't have any YT corresponding to it or YT minus 1 corresponding to it. Maybe this is the point where the time series has started. So when you regress these two and try to plot YT minus 1, which is on the x-axis and YT on the y-axis, and when you plot it, you will find a line and that line equation is beta naught plus b1 into YT minus 1. But when you plot y against time, see when you plot YT against YT minus 1, when y-axis is YT and x-axis is YT minus 1, you will see a line. But when you plot y against time, what you will see? If it is, what you will see? You will see a line? Will you see a line? So what you will see? What you will see? But what you will see, even you will see points here. It doesn't matter it is a point or not because you can represent a line. But what you will see, what would be the pattern of y? You will see this. You will see something which is going like this. That's what we discussed in the covariance stationarity. So until unless you don't see a mean reverting graph, you cannot even start thinking about AR model. And what is that horizontal line? What is this? This horizontal line, what is this? This is going to be your mean. Now the question is, luckily somebody did a research, okay, did a very thorough research and given you a time series model where it says y t is equal to zero point 0.5 plus zero point 0.8 into yt minus 1. Okay, and definitely error term. Somebody is saying that okay, there is stock return in the world which is following this equation that yt, that stock return of today is dependent upon the previous day stock return into a coefficient value of zero point 0.8 and zero point 0.5. Okay. So say the previous day stock return was 2%. So what would be the today's stock return based on this equation? So today's stock return would be zero point 0.5 plus zero point 0.8 into 2. So 1.6 plus zero point 0.5 is going to be 2.1% is my prediction. But definitely there is an error, and that error will either increase or decrease the y value. Say the error is zero point 0.2 further. So the actual y, this was y hat, the actual y is going to be 2.3. Okay. Now the question is, what is the mean? What is that long-term mean on which this y is mean reverting? Somebody gave you that AR model, but what is that long-term mean? How can you find that long-term mean? This is the question. A very simple question that I'll ask, that if I plot this, what would be the long-term mean? Can you see the long-term mean in this plotting, which I plotted here? I plotted this time series. What would be the long-term mean intuitively? Yes, it is going to be 50. Check. It is going to be somewhere around 50. The way I have taken the points is like sometime above, sometime below, sometime above, sometime below, that on an average it will come to 50. But if you don't have the time series, if you have this equation, somebody comes and say, hey, this is the equation that I derive from a time series yt, which I'm not going to tell you. Can you find the long-term mean? The answer is yes, you can find the long-term mean. What do you have to do? Step one, take mean both the side. Take mean both the side. If you take mean both the side, then you will write yt bar is equal to zero point 0.5 mean plus zero point 0.8 into yt minus 1 mean plus error term mean. What is the mean of a constant? It's a constant value itself. So yt mean, this is now yt mean or y mean. Y mean is equal to 0.5 plus 0.8. What would be yt minus 1 mean? What is yt mean and what is yt minus 1 mean here? What is yt mean? 50. What is this mean? 50. And why it is going to be 50? Because I'm saying that covariance stationarity has to be respected. The mean is stable or and constant. If the mean is not stable and constant, you can't use the AR model. So yt minus mean should be equal to yt mean and is equal to yt minus 2 is equal to yt minus 3. So basically, whether if I'm saying y is covariance stationary, if I'm using this term, the first thing is mean is stable. What is the meaning of this? Mean is stable. It means yt mean is equal to yt minus 1 mean is equal to yt minus 2 mean or yt minus k mean. Any lag. It is going to be constant. So it is going to be y mean. And what is the mean of error term? 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 Error term follow what process in ARMA model? Error term follow what process in ARMA model? White noise. What is the meaning of white noise? The mean is zero and a constant variance. So coming back to the flow chart, what I said, design ARMA model, but the error term follow Gaussian white noise. But what is the meaning of white noise? What is the meaning of white noise? That the mean is zero. So what is the mean going to be? Zero. So this is zero. Y mean, Y mean. Can you find Y mean? Y mean is equal to 0.5 upon 1 minus 0.8. So it is going to be zero point 0.5 upon zero point 0.2. It is going to be 2.5. That is your long-term mean. That is your long-term mean. And that is the formula they have written here in your curriculum. They haven't talked about how to prove it, but this is what it is. The mean is beta naught upon 1 minus b1. The way AR model is written in your book is very complex. It is written as yt is equal to delta plus phi 1 into yt minus 1, which we are in a very simple terms writing it as yt is equal to beta naught plus beta 1 into yt minus 1 to make the complexity simple. So this is what they have written. The theoretical mean, and definitely it is going to be a theoretical mean. So theoretical mean is mu is equal to beta naught minus b1. Why theoretical mean? Because what I said, when nobody is going to give you a time series and you have a AR model, then you can derive your long-term mean. But actually you can find the mean based on what? The time series. You take out the time series and find out the mean. Okay. So this is your theoretical mean. Now, I will introduce a very important concept here. Are you understanding thematically? Don't understand anything, but are you understanding thematically that your y has to be mean reverting? Then only you can use AR model. Can you understanding? Are you understanding this thematically? It has to be mean reverting. It has to always come back to mean. Why? Because we talked about what? Covariance stationarity. If y is increasing perfect, but it has to fall to y, mean. If it is falling perfect, but it has to be again coming back to mean, then fall whatever you want to do, but it has to be mean reverting. Are we understanding this point? Otherwise, we cannot use AR model. So AR model is only valid for entity which are mean reverting. What are the entities in the world which are mean reverting? Which is the best example? Which is the best example of mean reversion? Which statisticians and researchers has proved that most of the time this entity is mean reverting? What are they? Can you say that yes or no, that are you understanding that you can only use AR model when the entity is mean reverting? Okay. Now tell me which entity in this world, which we all know. from our childhood. That is mean reverting. Good. Temperature. What else? In finance term, interest rate in the market. When you look into the interest rate for a very long period of time, like 10 years, 15 years, it is always mean reverting. What else? Which you haven't seen properly, but inflation. Yes, definitely the temperature in India, it is generally mean reverting. What else? Stock returns are found to be mean reverting, not stock prices. Stock prices are sometimes mean reverting, not always, but stock returns are generally mean reverting. And tell me if the stock return, if you know and tested for few stocks, if it is mean reverting return, can you not predict the stock price? You can predict the stock price, right? A lot of, how many of you have ever seen technical analysis being done? The technical analysis chart. A lot of technical analysis charts, if you go into the background and try to find out that how the models are behaving, and if you try to find out actually inside, thematically they're talking about time series analysis, but not statistically, not with the universal law of statistics. Okay? So wherever you find that things are mean reverting, you can use the model. Yeah, definitely. Exchange rate is also one of the best example of mean reversion in long term. Okay. So if it is mean reverting, it is quite intuitive to anybody ask a question, what is the long term mean? The answer, I said, that long term mean formula, the long term mean formula is beta naught plus 1 minus b1 or theta, delta 1 minus phi 1 if the equation is y is equal to beta naught plus b1 into yt minus 1. Now here I shouldn't introduce something, but I will introduce a very important concept. Tell me a number, tell me a number which this b1 cannot take or this phi 1 cannot take. Good, that is 1. So your b1 cannot be 1. Your phi 1 cannot be 1. Your coefficient to yt minus 1 cannot be 1. This cannot be 1. And it is 1. Your mean is going to be what? Can you tell me what is the mean value? If I keep my b1 as 1, what will come as? B naught upon 0 will become what? Infinity. If it is infinite, is your mean stable and finite? If your mean is not stable and finite, can I say y is covariant stationary? No. Mean has to be stable and finite. Mean has to be constant. If it is not finite, if it is infinite, definitely it is not mean reverting. If it is not mean reverting, if it is not mean reverting, then I'm asking a question. Is it mean fleeing or mean explosive? Or this is completely random? Which option I should tick? Think very carefully. You're saying yt is equal to beta naught plus b1, and you're saying b1 is equal to 1. If b1 is equal to 1, then mean will come infinite. If mean will come infinite, then it is mean explosive or mean fleeing. Mean explosive or explosive time series or fleeing time series, or should you call it completely random time series? Okay. When something has a mean of infinite, what it means? Infinite means a large number, or it means which you cannot predict. What infinity means actually? Is it negative infinity or a positive infinity? You don't know. If it is infinity, you don't know what is beta naught. When I say infinity, here infinity is correct. Can't predict. If I'm saying can't predict, if I can't predict anything, it is going to be random. So the answer is randomness. So when I say B1 is 1, 1 stands for what? Unit, and B1 stands for root. If there is a problem of unit root, have you heard this term in this session? If there is a problem of unit root, can I use, have you heard this term? Yes, you did, which was the flowchart. So the flowchart says if there is a problem of unit root, then if the problem persists, you cannot use you cannot use ARMA model. You have to fix it. You have to resolve it. That is another thing. But if you cannot resolve it, you cannot use ARMA model. So you have to fix the problem of unit root. And how you find whether there is a problem of unit root? How you find the problem of unit root? When b1 is equal to 1. Perfect. When b1 is equal to 1, there is a problem of unit root. But for this time, the b1 came equal to 1. If I redo the calculation, b1 is not equal to 1. It is coming to 0.98. Next time it is coming to 1.2. Next time it is coming to 1.3. Next time it is coming to 0.8. So how to test it? How would I test that b1 is actually equal to 1 or not? How would I test it? How would I test it? So what I'm saying, I got the time series for 10 days. I got the time series for 10 days, or whatever the time series it is. I got my yt is equal to 0.5 plus 1 into yt minus 1. The next time I took another 20 days data point, my time series came as yt is equal to zero point 0.8 plus zero point 0.6 yt minus 1. The next time I did the testing, it came to yt is equal to, for next data point, like 30 data point, it came to 0.7 into zero point 0.9 into yt minus 1. Now my question is, how would you know that b1 is exactly equal to 1 or not? How would you know that statistically? How would you statistically prove that b1 is equal to 1? You got the question, yes or no? First of all, you understood the question or not? Hmm. What I'm saying, you took 10 data points. You took 10 data points and you tried to derive the equation, this one. You got your yt equal to 0.5 plus 1 into yt minus 1. Now you increase the data point to 20. Here b1 is what? 1. But for 20, your equation is coming to 0.5 into 0.8 into yt minus 1. You understood this section? Now the third time series that you are taking, that is for next to the next 10 data point, any random 10 data points in a sequence, it is giving you yt is equal to 0.5 plus 1 into yt minus 1. Now my question is, sometime it is coming as 1, sometime it is coming as zero point 0.8, sometime it is coming as 1 again, sometime 0.6. How would you test, how would you confirm that b1 is equal to 1 or not? What you do? What you will do? Is the question clear? Is the question clear? So do you remember in regression, do you remember that you did something where you tested the coefficient? How you tested the coefficient? How you tested the coefficient? You did a hypothesis testing. Do you remember that you did a hypothesis testing? Same way here, you have to perform a hypothesis testing to confirm if B1 is equal to 1 or not. 1 or not. The name of that testing is called as Decay-Fuller test. What test? Decay-Fuller hypothesis testing. The full name of this test is Augmented Decay-Fuller test. Decay-Fuller test. Now this test will tell you, we'll enter into the test, that is not important. And I haven't seen any question asked on Decay-Fuller test in depth and why it is called as augmented Decay-Fuller test in the last 10 years. But what is important that how you test it, that B1 is equal to 0, Decay-Fuller test. If it says yes, yes, B1 is equal to 1, then you confirm that your time series is what? Your time series, your Y is what? Y is what? Your Y is random. Good. Or you say your Y is stochastic. What is your Y? Stochastic. It is not deterministic. So basically, when anybody says that there is a problem of unit root, they talk about random walk. They talk about random walk. And that random walk is shown mostly in what entity in this world? What entity shows a random walk? You all know that. Stock prices. The most random thing on this planet is stock prices. And therefore, it is so random. It behaves so randomly. Therefore, you apply stochastic process to predict it. Okay? So therefore, you study stochastic calculus. What is randomness? Randomness is a state where whether the entity will go up or down, you can't predict. You can't say where the entity will go. And that is the randomness we are talking about. Which direction, which amount, you can't predict anything. And therefore, in the stochastic process, generally people write that yt is actually dependent upon the previous term yt minus 1. Previous term yt minus 1. Why we write the previous term yt minus 1 for randomness, that the next stock price is going to be the previous stock price? I have written yt is equal to yt minus 1. For what? Stock prices, which are kya? Which are completely random. Why have written yt is equal to yt minus 1? I have written yt is equal to yt minus 1 because if I have to predict something which is completely random, the best estimate for that random entity is the previous value. It's not the mean because it's random. The best estimate is the previous value plus a shock. This is an equation. This is an equation of a stochastic process. Why it is stochastic? Because it is random. Why it is random? What is the coefficient of yt minus 1? What do you see the coefficient as? 1. If you see anything else apart from 1, it is not stochastic. It can be mean reverting or it can be mean fleeing. It can be mean reverting or it can be mean fleeing. Actually, when B1 is greater than 1, when B1 is greater than 1, most of the time it is explosive time series, which means that yt is continuously increasing. And if you write the modulus of B1 is greater than 1, it means either it is continuously increasing or it is continuously falling. So you apply what? Trend model. But when you find B1 is less than 1, not equal to, because equal to you cannot write, because if you write equal to, it means it is random. You can't predict anything about it. But if it is less than 1, it means that it is going to be mean reverting. So I don't know whether it has been written here or not. Yeah. For the stationarity of AR model, the coefficient should be less than 1. Otherwise, it is not stationary. If it is greater than 1, it is going to be either increasing or continuously decreasing. It would be exponentially linear trend. I don't know. We can't predict until unless we do a proper testing of the model. So B1 has to be less than 1 or greater than minus 1. If it is not, you cannot use AR model. Okay. So actually, we said a lot of thing about autoregressive model. The first assumption is it has to be covariance stationary. What it means, the mean has to be finite, the variance has to be finite, the covariance has to be finite and stable, blah, blah, blah. But even if you are using this model, the B1, the modulus of B1 is less than 1. This is one property. The second is the error term has to be what? Gaussian white noise, which means that it has to be normally distributed with a mean of 0 and a constant variance. And it should be independent. If all these properties are not satisfied, you can't use AR model. Okay. Okay. So actually, we were only talking about mean. We were only talking about mean. But even this small concept of mean entered into the discussion of stochastic process, entered into the discussion of randomness and mean fleeing concept. So when B1 is greater than 1, you will have mean explosive or explosive time series. When B1 is equal to 1, it is random. When B1 is less than 1, it is a mean reverting time series. But there are other concepts that we have to discuss. That is to prove the variance of yt, where the equation is beta naught plus b1 into yt minus 1, or if the equation is written as yt is equal to delta plus phi 1 into yt minus 1, the variance equation is written as the variance equation of yt is written as sigma square error term upon 1 minus phi 1 square. The question is, can you prove it? The way we proved that the mean of this AR model is going to be delta upon 1 minus phi 1. Can we prove that the variance of y is going to be the variance of error term plus 1 minus phi 1 square? And this is only true for AR1 model. We are not talking about AR2 model, AR3 model. So we are only going for 1 lakh. That is, we are moving from YT to YT minus 1. So can you prove that? Yes or no? If not, then I'll prove right now. Let's prove. What we are proving? We are trying to find out what is the variance of YT if an equation of AR model is given as YT is equal to beta naught plus B1 into YT minus 1 plus error term. Same as mean, take variance both the side. Take variance both side, LHS and RHS. So variance of yt is equal to the variance as a sigma square of beta naught plus b1 into yt minus 1 plus et. There is plus required. So what is the variance of a plus b? Anyone remember what is the variance of a plus b? What is the formula? The variance of a square plus variance of b square plus, correct, 2 into correlation into standard deviation of A and standard deviation of B. Correct? This is the formula. So we have to expand it. Cool. So variance of beta naught square plus variance of B1 into YT minus 1 plus variance of error term. What is the variance of a constant? And plus into 2 into correlation between beta naught into B1 YT minus 1 into standard deviation of beta naught into standard deviation of B1 into YT minus 1, 2 into correlation between error term and B1 into YT minus 1 into standard deviation of error term into standard deviation of B1 into YT minus 1 plus 2 into correlation between error term into B1 into YT minus 1, sorry, error term and beta naught, sorry. I'm just expanding the equation. It's nothing complex, very simple terms. Okay, what is the variance of a constant? What is the variance of a constant? Zero. The constant cannot move. The variance of a constant is zero. A standard deviation of the constant is zero. Or the what is the correlation between error term and anything on the planet? Zero. So this is zero, this is zero. The correlation of a constant with anything on the planet, this is zero. So these terms are zero. You don't have to write it. So these terms are zero. So what is left with? The variance of B1 into YT minus 1 and the variance of error term, because the variance of constant is zero. So variance of B1 into YT minus 1 plus variance of error term, this is left. In the left hand side, we have variance of YT plus B1 is again a constant. And we know that when a constant comes out of the variance, it will become square. So B1 is square. So YT is equal to B1 square into the variance of YT minus 1 plus variance of error term. Variance of error term. What is the property of Y if it is covariant stationary? What is the second property? What is the second property? When I say covariant stationarity, what is the second property? What is the second property? The variance must be finite and stable over time. So my question is, will these two would be different or same? The variance of YT and variance of YT minus 1. Same. So variance of YT is equal to B1 square into variance of YT plus variance of error term. If you take variance of YT in the left direction, then it will come as what? 1 minus B1 square into the variance of YT is equal to variance of error term. So variance of YT is equal to variance of error term upon 1 minus B1 square. This is what is written here. Variance of error term, variance of error term upon 1 minus B1 square. That is what we have proved. Clear? The third thing that we have to prove or understand, which is actually complex, is the correlation structure between YT and YT minus 1, YT and YT minus 2, YT and YT minus 3. Super, super critical, super, super important, because this is related to